Alright, hello again today, and we're going to be looking at section 2.2, linear inequalities in one variable. Once again, recording from home. You may hear strange noises. I was trying to wait until the train passed before I started this video. So please disregard any of those. If you have questions, please email me, ask me over email. You can call my office. Alright, so linear equations in one variable. Solving linear inequalities, solving compound linear inequalities, and solving absolute value inequalities. I would edit all those mistakes out if I had the equipment at home, which I do not. Alright, inequality symbols. So here we have the following, where we have this symbol is read as less than, this is less than or equal to, this is greater than, and this is greater than or equal to. In other words, it always opens to the greatest number. Kind of learned something like that, I think, at grade school. Wants to eat the larger number. And then we say when this is equal, the linear equation is replaced with one. When the equal sign in a linear equation is replaced with one of the above inequality symbols, we obtain a linear inequality. The set of all values of x that satisfies such an inequality is called the solution set. For example, we have an inequality where we have 5 minus 2 times x minus 3 quantity is less than or equal to negative 1 minus x quantity. The negative of. Alright, compound linear inequalities. A linear inequality like x is greater than 4 states that x is greater than 4. Sometimes we want to say that x is greater than one number and is also less than a number. We can write this as a compound linear inequality. If we want to say that x is greater than 2 and also is less than 4, then we write 2 is less than x, which is less than 4. Remember, this should always make sense if you remove the center portion. 2 is less than 4. Note, this is exactly what I said just a second ago, when writing the compound linear inequality symbol, inequality symbols must always point in the same direction. I would say the same direction, and it makes logical sense. If both the inequalities were going in the opposite direction, where it said 2 is greater than 4, that would be wrong. You must make sure that it makes sense without the x in there. And so an expression like this, if you remove the x, that doesn't make any sense at all. 2 is less than, which is greater than 4, doesn't make sense. Inequalities can be written in shorthand notation called interval notation. To write a compound inequality in interval notation, list each endpoint with a comma between them or the smallest number first. Use brackets to indicate that equality is possible. In other words, you have these extra lines right here that correspond to these bars right here, or parentheses if we're just strictly less than or strictly greater than. So in other words, if we're non-strict, we can include our endpoints. We use brackets. Not including our endpoints, we use parentheses. When an inequality only has one endpoint, we write infinity or negative infinity for the other endpoint. Negative infinity is always written as the left endpoint, and infinity is always written as the right higher endpoint. Because infinity is not a number, we always use parentheses next to it. So infinity doesn't ever get a bracket for us. We always use parentheses because it's more like a direction than a number. Just keep going that way forever. So write each inequality in interval notation. So just looking at this, we're just going to write our 3 and our 4 because we're trapped between them, our x value. We give a parentheses to 3, comma, and a bracket for 4. So remember, parentheses correspond to this, bracket corresponds to when we're possibly equal. Here we have x is less than negative 3. To be sure, sometimes I tell students, write a number line, put negative 3 in here, and make sure you can reason it out. So negative 3 is the important point here. We want numbers less than negative 3. So which side of the number line are we on? We're on this side, like negative 4. So in other words, I want to shade everything to the left. So here we'd say that we want all the numbers from negative infinity, because those numbers are less than 3, negative 3, all the way up to negative 3. And we don't want to include negative 3, so it gets a parentheses. And here, the same thing for here. We mark out negative 4. We want x to be greater than or equal to negative 4, so that means we want to include 4 all the way up to positive infinity. So graphing on a number line is usually the safer bet, just to see exactly where you are. Compound inequalities is pretty easy to see where you are as long as it makes sense without your x in there. And so we're going to say negative 4, not including negative 4 for this last, including negative 4 all the way to positive infinity. So you have a couple exercises like that. Once again, so graphing inequalities, we can also represent intervals graphically on a number line. For numerical endpoints, we mark the same brackets or parentheses that we use for the interval in appropriate positions on the number line. For the endpoints of negative infinity or positive infinity, we shade the arrow at the end, on the end, indicating that the interval continues on without with no bound. So here, when you're looking at Hawks, you'll have these buttons down here, and some of them will be like parentheses, parentheses, bracket, bracket, parentheses, bracket, bracket, parentheses. I'm not sure exactly what order they're in. You pick one, whatever. But be sure, if you want to include, like, let's say positive infinity, let's say you're saying x is greater than 2. So we want all the numbers not including 2 all the way to positive infinity. You highlight this, and then it automatically pop up as the infinity. And so it would include that in your homework. But you'd have to be careful that you clicked the double parentheses here, because infinity always gets a parentheses. So make sure if you drag it to either end that side has a parentheses. So you have like, and then there's a button, I think there's for clear, if you want to clear your number line. At least that's how it was last time I did the homework last semester. They change things every semester, so when I reflect that, some students will be like, wait, it was different. If it's different for you, let me know. Alright, so graph inequality, pretty straightforward. Marking off the important points 2 and 3, and then we want all the numbers between 2 and 3. And you click that double parentheses button and Hawks, and then just drag it to 2 and 3. Those brackets and parentheses in Hawks appear at a random place on the number line, not always the same place. And if that's the case, you can accidentally have one of your numbers be selected as the right endpoint, and so just don't assume that the other endpoint is correct. Here we have a similar thing where we plot off 4 and 8. We use brackets and we'll shade in between. So you'd click the double bracket button here. Once again, we need a interval notation for this because there are an infinite number of points between 2 and 3. 2.5, 2 1/4, 2 3/4. All that stuff is inside here. There's an infinite number of points. So we just don't want to say 2 and 3, or this says nothing. There's an infinite number of points on the real number line between these two values. Here we have one where we'll mark off 1, and whoops, and I wrote 2 for some reason. We mark off 1, and then we're going to want all the numbers from 1 and then all the way to negative infinity. So here, so we're going to use parentheses. And so here you use a double parentheses button and Hawks. And then here we have this last number line where we want to plot off 0. We want to include 0 all the way to positive infinity. We shade all the way to there. Once again, in Hawks, you click on the bracket parentheses button to use that, and then you drag this parentheses all the way out to positive infinity. It would highlight it. I'll let you know. Here are basically all the different situations you can have. You can look through the sheet. You can pause the video here. But basically, these are your open intervals we've seen, closed intervals. We've done those half open intervals. You can have half open with regular points, or you can have half open intervals that go to infinity. You know, with your bracket. The other side's open to positive infinity, negative infinity here. Open intervals means that none of my endpoints are going to be included. Closed means including your endpoints. Open means not including your endpoints. Multiplying by negative numbers. So the inequality, negative 3 is less than 2 is obviously true. Oops. Apparently my volume for my computer's on. Thought I had that turned off. Hold on. Apologize for that. I thought I had my system sounds off. I did not. Alright, the inequality negative 3 is less than 2 is obviously true. If we multiply both sides by negative 1, the left side is going to be negative 1 times negative 3, which is equal to positive 3, and the right side is negative 1 times 2, which is negative 2. So now we have 3 is in some relationship to negative 2. In order to make this true, the inequality needs to be greater than. Notice that this is the opposite direction from the original. This illustrates the rule. If you multiply both sides of an inequality by a negative number, the direction of the inequality reverses. So we've probably seen this before, pretty, you know, in our previous math encounters, that we flip the inequality sign if we multiply by a negative number. And the reason because you're basically looking at the negative values of both. So you're going to rearrange everything and flip the inequality sign. So solving linear inequalities, the same way we'd solve a linear inequality, except that as we just saw, if we multiply or divide by both sides by a negative number, the direction of the inequality will be reversed. Our answer will be arranged. We arrange the numbers and not a single number. For example, solution written as x plus 4 is less than 3 would be x is less than negative 1, which is written as negative infinity to positive, to negative 1, not including negative 1. Solve the inequality and graph the solution set. So solving it like a normal one. Now, there's a couple ways you can do this. If you can look ahead into a problem, you can see which side is going to make the variable positive or negative. In this case, we have 5y here and 7y here. If we move the 7y to the other side, we're going to make the y's negative. That's okay. We'll just divide both sides by a negative number, have to flip the inequality sign. But if you look ahead into the problem, you're like, wait, I want to avoid that step. I could just subtract 5y from both sides and keep my y's positive on the right hand side. You can do that as well. You'll get the same answer back out. I'm going to work it how students typically work it and keep their variables on the left. So we're going to say 7y here, less than or equal to, oh sorry, don't want that yet. 7y here, and so that's going to give us negative 2y minus 10 is greater than or equal to 4. And so I'm going to add 10 to both sides. So we're going to get negative 2y is greater than or equal to 14. And then here's the key step. When I divide both sides by negative 2, what I like to do is I like to go and I like to circle my inequality sign to let myself know in the next step I'm going to flip it. So we're going to say this is y is less than or equal to negative 7. Any questions about that? That's what I always say in class, but I'm recording this, so yeah, y'all can't respond immediately. You do please email me if you have questions. So here, once again, just to make sure I'm on the right side of my equation, because sometimes you can write this in such a way where your variable's on the right-hand side and you're not really sure how to phrase it. I would just plot the important number. Here's negative 7. I want all the numbers less than negative 7. So numbers less than negative 7 would be numbers like negative 8, negative 10, so forth and so on. So I'm going to bracket that because I'm going to include that. I'm going to shade all the way down this way to negative infinity. I'm going to say all my answers are from negative infinity to negative 7, including 7. Not including infinity. It always gets parentheses. Now, assuming I've done all this correctly, Hawks will often ask you for the solution set before graphing it. I tell my students to graph it before the solution set because it's easier to look at the graph and find the solution set than the other way around, because if you get the solution set wrong, you're probably going to get the graph wrong, and it's easier to get the graph correct the first time around. Here we have a compound inequality, so the first thing we're going to do is multiply everything by the denominator here, negative 2. And so when I do that, I like, once again, to circle my inequality signs to let me know in the next step I'll flip them. And this is also multiplied by negative 2 here to get rid of that denominator. And so when we do that, so whatever you do in a compound inequality has to happen to all three parts. So this is going to be 8, which is less than, oh, I said I was going to flip it. So it's going to be 8 is greater than x plus 2, which is greater than or equal to negative 2. Once again, you can always make sure that you flip them correctly or you didn't forget, because if you put this, if you make the middle part disappear, 8 is greater than negative 2 is a true statement. So I'm going to subtract 2 from everything now to get my x by itself. So I'm going to get 6 is greater than x, which is greater than or equal to negative 4. X is by itself now, and once again, I'd write it on a number line because I see students so many times, they'll look directly at this and say 6, parentheses 6, comma, negative 4, bracket, and that will be wrong because your interval notation needs to appear exactly the same way it appears on a number line. So in other words, I want to include negative 4 all the way up to 6, not including 6, so I want negative 4 to 6. And so that's my interval notation. A lot of students will get it backwards. If your numbers in your interval aren't in the same order they would appear on a number line, it will be counted incorrect. By not only me, but these software as well, and courseware, and most other math teachers out there. So now let's look at how we solve absolute value inequalities. So here we have the absolute value of x is less than 4. So we can find all the solutions where x is not negative by solving x is less than 4, because x is not negative. The solution set is 0 to 4. If x is negative, because you know it can't be negative, it's an absolute value. If x were negative, then we'd have x equals negative x. So we need to solve negative x is less than 4. This is the equivalent to x being greater than negative 4, and the solution set is negative 4 to 0. So this becomes the situation where we have to get all the solutions. We combine the two inequalities where we want all the values less than 4 and all the values greater than negative 4. And since we have an and, we can combine these two into one interval, or a compound inequality or double inequality. And we have negative 4 is less than x, which is less than 4. The solution set is from negative 4 to 4, parentheses on both sides. Graphically, this is represented below as negative 4 and 4 shaded in between. And here, I like to think of it, what we have here is this is 4 units away, and this is 4 units away. And so we're within 4 units of whatever's inside. Here it's x, so it's going to be 0. 4 units is 0. 4 units inside of whatever that bracket is. So if c is positive, then we take the absolute value of ax plus b is less than c is equivalent to ax plus b is greater than c, and ax plus b is less than negative c, or compoundly. Excuse me. So I think that's backwards. How do I look at it? That seems strange to me. Yes, it's a cut and paste error. That is in the wrong direction. That is a cut and paste error. Let me correct that for you all. Correct this in your notes. So we're less than c, and we're greater than negative c. In other words, more compactly, we're between negative c, ax plus b, and that's less than c. It's also true when we replace the less than by less than or equal to. So here you're going to be trapped between two values of c, negative and positive c. In other words, whatever is within c units. This expression is within c units of x, whatever it is, that expression. Whatever that means. And so here we're going to get it in standard form first before we can do anything. Divide both sides by 4. We get y plus 4, absolute value of that is less than or equal to 12. Not 12, I just said divided by 4, didn't I? 3. And so we're going to have a situation where we have, it's less than, I'm going to be trapped between the values of negative 3, less than or equal to, y plus 4, which is less than or equal to positive 3. So now that we have that, we can solve all these at the same time. Negative 4, negative 4, negative 4. And we have negative 7, which is less than or equal to y, which is less than or equal to negative 1. And once again, I always want to graph these first to make sure that I'm getting my numbers in the right order, because negative 7 does come before negative 1 on our number line. We want to include our endpoints. This is an AND statement. And so we're going to say we want all the values from negative 7 all the way to negative 1. And that is our solution set in interval notation. Once again, we want to write it in normal form here. We're getting nice integer numbers as our endpoints. You could get fractions, totally fine. Just want to let my students know that. Here we want to get it in standard form first, so I'm going to subtract 12 from both sides. So when we do that, we get 3, and then we get x minus 2, and that's going to be less than negative 12. And we can keep going, divide both sides by 3 to get it in standard form. And so we get the absolute value of x minus 12. These absolute value symbols look a little bit better. And that's less than or equal to negative 4. And here's where you can stop and look at this and say, if I have this in standard form, this needs to be a positive number of 0, because I can't have a negative distance. This is negative distance. which is not allowed. So negative distance not being allowed, this is not going to have a solution. It's going to be no solution. Now, what happens here is hawks will often, in practice, not for the answer. For the answer, you can just click the no solution button. But in the practice or step by step, is that they'll tell you to solve this and then check your work and show that your answers don't check out. Your answers don't solve the equation correctly. And you can do it that way, but that's a lot of work. If you want to, you can. But that's how hawks will show you. So be aware of that. Some other places online, if you go to other websites to look at how to solve solutions, or they will tell you to solve this anyway, then check to see if you have the right answer and show that you don't have a right answer, so it's no solution. And so I would prefer just to stop here at this point if you have it in standard form on the left and this is on the right. So absolute value inequalities part 2. Here we have a greater than symbol. So we're going to solve for when the absolute value of x is greater than 4. We can't find all the solution where x is not negative by solving x is greater than 4. The solution set is 4 to infinity. If x is negative, then the absolute value of x is equal to negative x. So we need to solve for negative x is greater than 4. This is the equivalent to x is less than negative 4. And the solution set is negative infinity to negative 4. So here we want to be more than 4 units away from 0. So either I want to be from 4 to positive infinity or negative 4 to negative infinity. So here, if we were to draw this on a number line, we mark off 0, we mark off 4, 4. I think that's on the other page. I'm getting ahead of myself. And basically, we want to make sure we're more than 4 units away. 4 units away from 0. I think I actually wrote this on the other slide. I did. To get all the solutions, we combine the two inequalities with an OR statement where we want to be x is greater than 4 or x is less than negative 4. The solution set negative infinity to negative 4 union 4 to infinity. Graphically, this is a representation below. I'm 4 units away in either direction from 0. This is positive. The absolute value of ax plus b is greater than c is equivalent to ax plus b being greater than c, it's written in the correct direction this time, or ax plus b is less than negative c. This is also true when less than is replaced by less than or equal to. Real quick, I want to check the other one to make sure it had the and statement. Yeah, it did. So solve the following equation and graph the solution set. Once again, I always graph the solution set first, but more on that later. So we subtract 3 from both sides, and I'm going to get negative absolute value of 4y, and that's less than or equal to negative 16. Once again, we're not done yet. This negative 16 isn't in standard form, so that negative over here might cancel, and here it does. I'm going to multiply both sides by negative 1. And if I multiply both sides by negative 1, what happens here next is I have to flip my inequality symbol. So that's going to give me the absolute value of 4 minus 4y is greater than or equal to 16. So in other words, I'm in a greater than situation. So I'm going to have two situations. I'm going to have 4 minus 4y is greater than equal to 16, or I'm going to have 4 minus 4y is less than or equal to negative 16. Once again, I have students that would change the sign on the left-hand side of both these instead of this one. I prefer the right hand. There's only one sign to change. So here we're going to subtract 4 from both sides, and we're going to get negative 4y is greater than or equal to 12. And so I'm going to divide both sides by negative 4. When I do that, I need to switch my inequality sign again in the next step. So it's going to give us 4 is less than or equal to negative 3. Sorry, y, not 4. Next, I'm going to subtract 4 from both sides here, and that's going to give me negative 4y is less than or equal to negative 20. And so I'm going to divide both sides by negative 4. That's going to flip my inequality sign. So I'm going to get y is greater than or equal to positive 5. And so I graph this on a solution on a number line first and say this is -3 all the way to 5 here. I want all the numbers less than -3, and I'm going to include that -3. I want all the numbers greater than 5, and I'm going to include that 5. And so now I'm going to have negative infinity all the way up to -3, including that union 5 or bracket 5 all the way up to positive infinity. I'm going to give a parentheses for that positive infinity. And this is my solution right here. Alright, here we have another one. So what we're going to do here is get it in standard form, as always, first. So I'm going to subtract 3 from both sides. Seems to be pretty much the same start as before. We're going to have that greater than a -16. I'm going to divide both sides by 4 to get it in standard form. So I have the absolute value of y minus 2. And that's going to be greater than, I don't need to flip the sign, I'm not dividing by a negative, and that's going to be -4. Now here's the interesting part. Before, when we said we were less, this is negative distance, right? Negative distance. It doesn't make any sense. But this says right here, this is supposed to be positive. Or 0. So how often is my positive number greater than my negative number? Negative, I should say. Let's not talk about distance right now. My negative number. Well, positive numbers are always greater than negative numbers, so this is always true. And so it's going to be all real numbers. And basically what happens here is when you go to graph this, you're going to find, if you were to continue on with the equation, you're going to find out that you're going to have two instances where you're going to have you overlap when you do the OR, and you end up getting the whole number line back out because it's an OR instead of an AND. So that'll be all real numbers. So anytime you have that negative on the right hand side, standard form on the left hand side, you're going to be in a no solution equation if you're less than a negative number. If you're greater than a negative number, it's going to be all real numbers. So these geometric interpretations, if we solve for the absolute value of x is less than or equal to 4, this is a set of all points where the distance from the origin is less than or equal to 4. Graphically is represented as follows. I mentioned this before. If we solve that the absolute value of x is greater than 4, greater than or equal to 4, this is a set of all points where the distance from the origin is greater than or equal to 4. Graphically, it represents the following, where we want to be more than 4 units away. We lay these two sets on top of each other. We see that they cover the entire number line. The solution set for when we're less than or equal to 4 is the same. The solution set for the absolute value of x as less than or equal to 4 is the set that is closer to 0, and the solution set for when x is absolute value of x is greater than or equal to 4 is the set that is further away, the points farther than 4 units away from 0, including 4. Any compound inequalities is called a compound inequality. Any combination, of two inequalities is called a compound inequality. And here we have x is less than 4 and x is less than -3, or x is less than 4 or x is less than -3. So we have an and statement or statement. When we write an and, the solution set where both have to be true at the same time. We write or, we say the solution set where at least one of them is true. An efficient way to solve a compound inequality is to graph the solutions to both inequalities. If they are joined by an and, the solution set for the compound inequality is where the shaded regions overlap. If they are joined by an or, the solution set for the compound inequality is everywhere that is shaded. So here we want to solve inequality by representing our answer in interval notation and graphing the solution set. So here we don't have to solve our equations. Sometimes you have to solve an equation before you can do this. But here we're going to have, so I'm going to get one number line. I'm going to mark off -7 and 6 because those are important points. And here with one color, let's see if I can get two opposing colors here. So what we have here is we want all the values that is less than or equal to 6. So in other words, we want to be on the left side, so I want to include 6. And then we want all the values that are greater than -7, not including 7, -7. So it's an and. And we want the overlap. So I want from here to here. So my solution set is going to be from -7 to 6 on our number line, parentheses, bracket. And so here we have -7, parentheses, -7 all the way to 6. Next one, we're going to have an OR statement. So we're going to have our number line, mark off our important points, -6, 2. So in other words, I want all the numbers greater than -6, or sorry, yeah, x, sorry. Let me say that again. I want all the numbers where x is less than -6. So in other words, I'm over here. X is less than -6. All the numbers to the left. And then I want or all the numbers less than or equal to -2. So if I want this, I want everything that's shaded. So all the regions that are shaded are going to be from 2 all the way down to -infinity all the way up to 2. So it's going to be -infinity all the way up to 2 in this case. And that's going to be your. So Hawks will have questions like this, and when they give you questions like this, usually it truncates down to one interval. There are silly situations that can happen. Silly situations are as follows, where you could get an AND statement, where you have an AND statement and they don't have any overlap, and the AND would give you the empty set back out. Or they could have an OR statement where they overlap on both sides, everything, and you get all real numbers back out. So watch out for that as well. You could get an OR statement where it looks like this, and so you get the whole number line back out. Or you could get an AND statement where they don't touch, there's no overlap, and you get empty set back out. Rarely happens, but it is possible. Sometimes they generate silly problems. Applications of inequalities. Inequalities frequently show up in application problems. Grades are a common example for it isn't important that the average grades are one common example. It isn't important that the average be exactly 70% to earn a C. Actually, anything greater than that will do. When translating application problems into inequalities, be careful that the conditions were assumed to be true and not stated. For example, in the problem involving tests, it's not usually possible to earn more than 100% or less than 0. So in your homework, you could be asked how to solve an inequality problem, including test averages or something like that. And if you find out that you can get an A somewhere between this and this, you may get a solution back out that's more than 100%. Well, you want that right-hand boundary to be less than 100% or equal to 100%, no more than 100%. So watch out for that in your homework. It would be something like this where you get like, you average up 4 test values. Yeah, 4 test values, and you want that to be greater than, let's say, 90%. And so doing that by 4, you're going to find out that maybe the test you need to be maybe have to be greater than like 106% or something like that. And that's not going to happen because you can't score over 100, so that would be no solution. So that's I don't know if that's true or not. I'm just making up an example off the top of my head. So watch out for that. The perimeter of a rectangle must be less than 150 feet. If the length is 72 feet, find the range of possible widths for the rectangle. Express your answer in interval notation. Use decimal forms for numeric values when needed. Alright, so it says we have a rectangle. So that's going to be 2 times length plus 2 times width equals perimeter. And we want that perimeter to be, we want P to be less than, it just says less than 150 feet. It doesn't say less than or equal to. It just says must be less than. So we assume the perimeter has to be less than 150 feet. And so we say the length, we give L being 72 feet. Then we're going to have the following. 2 times L, 72, plus 2w has to be less than 150. You can draw a picture for this if you want. This would be our width. This would be 72, which is our length. And I think this one comes out to a very interesting, very small number. It happens. So we're going to have 2 times 72. And so that comes out to 144 equals 2 plus 2w. Well, it has to be less than 150. And then we're going to subtract 144 from both sides. And so that's going to give you 2w equals 6. So that means divide both sides by 2. I'm sorry, this is still less than. And this is going to be w is less than 3. So in other words, I have, my answers could be all the way from, so if it must be less than, I would say that to find the range of widths of possible rectangles in interval notation, then it would be 0 is the least amount it could be. And 3 would be the greatest amount it could be. Less than, strictly less than 3. Now, this problem, when it was placed in the homework, I think we modified this question in the homework to where this was more than 150 feet, because it didn't really make sense. Because if you had 0, you wouldn't make sure you don't include 0 here. It was ambiguous. If you include 0 here, then it wouldn't be a rectangle at all. It would be a line. So you have to be careful with that. But yeah. All right. So that is the lecture for today. Watch those test averaging problems and your percentage range to be understood. The other thing I like to make sure students know about are implied constraints. For example, if they give you like people, if you're measuring people or you're measuring amounts, you can't have negative numbers of things like people. You can have negative money, being a debt and whatnot, but you have to make sure that the quantities you're dealing with, like you can't have, you know, a negative amount of cars or a negative amount of people, or if you might only be able to deal in whole units. Not necessarily in this class, but sometimes getting half a person doesn't make sense. You have to round it to some value, either above or below, to get a whole number back out. But that is the lecture for today. You all have a great one.